All right, everyone, welcome back to Calculus 3. So just a little announcement. So number 18 on the exam last Friday was messed up. I think it had like the wrong format for the question. So everyone's just going to receive credit for that. And even before that, though, the average on this exam was better than the last exam. So nice job, everyone. All right, so now let's go ahead and get started. Well, not quite started, but let's continue studying this, the material from the third part of the class. Last time we had new material, we talked about double integrals, which is essentially trying to find the volume underneath a surface. So we were able to do that so long as our region of integration was a rectangle, like we had a number to a number for x and a number to a number for y. But it turns out that we're going to be able to do these double integrals for more than just rectangular regions as well. So let's say maybe we wanted to find the area under this surface for this kind of oddly shaped region D right here. So how are we supposed to figure that out? Can we still use double integrals to do that? And the answer is yes. What we're going to do is we're going to define a new function over a rectangle that contains D. So let's imagine that this is our rectangle and it contains D right here. All right, so then what we're going to do is we're going to do a rectangular integral or a rectangular double integral over R with capital F of x, y. All right, now what's this going to be? This is going to be a kind of a funny piecewise function. If we're in the region D, then we're going to agree with little f. Yeah, I can't write a comma. There we go. So if we're in the region D right here, then we're going to match our little f function right here. Now, if we're not in the region D, what we're going to be is we're going to be 0. So this way, when we're integrating, we don't get any volume over the parts that the rectangle doesn't intersect with D right here, but then we're just going to get the normal function for D. So we've effectively turned our kind of weird integral into a rectangular integral by using this. So to summarize in an equation, if we want to do the double integral over some non-rectangular region, what we can do instead is integrate this new capital F over the rectangle R, and this would be our R here, that would contain that region D right here. Now, this is more or less a formality. This isn't really how we're going to be doing double integrals. This kind of just justifies that we can do a double integral over a region that isn't quite a rectangle, or maybe not rectangular at all. So now we know we can do these, but we're not going to, in practice, break up our functions into this piecewise thing where it's 0 outside of our domain and the function inside. All right. Okay, so if we're not going to do it that way, how will we actually do it? What we're going to do is we're going to kind of keep the same philosophy with the iterated integrals, where we do an integral with respect to y, and then we do an integral with respect to x, or the other way around. We could do an x first and then a y. Okay, so there's type 1 double integrals where we do the integral with respect to y first. So what we do is for our boundary, rather than having a fixed number, we're instead having a curve as our boundary. So these are our two boundaries for y. So g2 of x would be our upper bound, and then g1 of x would be our lower bound. So our first integral that we're going to do goes from g1 of x to g2 of x. And since we're integrating in the vertical direction, then we're going to be doing this with respect to y right here. All right. And then once we do that, here's the philosophy that I want you guys to have for the rest of this chapter here. So pay attention to this. It's going to be important. So whenever we do one of several integrals in a row, what we imagine happens after we finish the integral is that dimension kind of compresses into just one point. So since we just did the integral with respect to y right here, we're going to kind of compress the y dimension. We're almost going to kind of squish this shape down here. You can't see, it's still on the screen here. I don't have anything below that. So we're going to crush this shape down flat, and then we almost kind of imagine that we have like a line that we kind of made in the middle, like we crush this shape down to just a thin line. Then for our next integral, which is going to be an x integral, what we do is we look at the lowest point that we have here, which is a, and then we go to the highest point on this line, which will be b. So the first part of our integral will be 1d curves, so something that we draw like a function, and then the next part where our boundary will be zero-dimensional points. So every time we do an integral, we kind of squash one dimension and then continue doing integrals until we get to points as our last bound. All right, now this squashing doesn't have to happen with y as the first dimension and then we do x. It could go the other way too. So we could have our x bounds as these curves here, though this time they'd be a function of y instead. So we would first do the integral from h1 of y to h2 of y, where the left one counts as lower because those will have a lower x value. So we do h1 of y to h2 of y of f of xy dx. And then what do? Then we crush this dimension down into nothingness here, and we just pretty much have a flat line. And what are the boundaries on this flat line? It'll be these 2 points right here. And these are 2 different y values, c and d. So we could also do the integral the other way as well. Yeah, simply crush the dimension. Yeah, I guess it kind of sounds, like a big thing to do, but really you're just imagining that you don't care about this direction anymore and you only care about the directions for which you have d whatever remaining. All right, now notice that just like we had last time, as long as our function isn't too bizarre, like usually if we have a continuous function, then we're going to be able to integrate this in either order. So you would get the same result that you would get from here as you would right here. Now, the thing is that unlike last time where it was just, the bounds were just numbers either way, very often it'll be the case that one direction of doing the integral will be much easier than doing the other version of the integral, even though in theory they both give the same amount of, the same value. Sorry, I'm kind of distracted here. Let's see. What if it's not flat on one of the ends like these are? Oh, so like if it's kind of like curvy or something like this? We'll get to that in a little bit. Don't worry about that. We'll get to that in a little bit. We're going to have a lot of ways of dealing with strange regions for our integrals. In fact, we'll see stuff like this today. All right, so let's do a simple example here. So find the double integral of 5dA over the region D, where D is the triangle with vertices 0, 0, 0, 4, and 1, 4 right here. All right, so let's draw what that looks like. So here's 0, 0, here's 0, 4, and then we have 1, 4 right here. All right. So what I'm going to do is I'm going to do this problem twice. And the first time I'm going to do it, I'm going to do where I do the y, the dy first, and then the dx, and then I'll do it the other way around for the next part of the integral. All right, so for my first part of the integral, I'm going to integrate 5, and I'm going to do dy and dx. All right, well, let's see here. So we need functions y equals something, and then y equals something here. So let me ask you this. What's the function for the top bit here? What function is that? Y equals what? Y equals 4, that's right. Now you may think of the, oh, that's just a number, that's a point. I thought we were supposed to get to those in the next integral. Well, this is not just a point 4, this is the constant function 4. So this is actually a function, even though it's written as just a number here. And that's totally fine. All right, now what's our lower function here? What's the equation for this diagonal line? Yeah, it's going to be 4x, that's right. All right, so our lower bound, the thing that's lower with y, is 4x. Okay, now let's imagine that we did that and we crushed down our dimension here. If I kind of squeeze this together, if I did that, what would my x bounds be? What's the biggest x value we have? What's the lowest x value that we have here? If we kind of squish in the y direction. That's right, it's going to be 0 to 1. There we go, because the lowest x value we have here is 0, and the highest x value we have is 1. All right, and then once we do that, then we're just doing an iterated integral. So we do the integral with respect to y first, and then we do the integral with respect to x next. So let's see, the integral of 5 with respect to y here. What is the 5? It's from the problem. We're integrating 5. So we integrate 5 with respect to y. So we end up with just 5 times y. Now for my bounds, I have 4x and 4. Now, even though these are functions now, we still plug them in exactly the same way that we would previously here. All right, so we plug 4 into here. 4 times 5 is 20. And then we subtract and we plug 4x into here. And we have 20x. All right, and then finally we have one more integral. Now that we've squished this dimension, we got rid of the y, now we just have the x right here. So I'm going to integrate 20 with respect to x and get 20x. I'm going to integrate 20x with respect to x and get 10x squared. Now we'll go from 0 to 1. So we plug 1 into here and get 20. We plug 1 into here and get 10. And then plugging 0 into either of these will give us 0. So our grand total of our result right here is 10 right here. All right. Let's see. Looks like we missed a question here. Why was 4x used instead of 0? Because 4x was our lower bound for y right here. So we have our upper function for y, and then we have our lower function for y right there. Should you only have the variables that match the integral to know you did the integral right? Yeah, so we shouldn't, after we do the y integral here, we shouldn't have any more y's floating around. We should only have x's. So yeah, that's a good point. Just be aware of that. So there shouldn't be any y's once we finish this integral. Okay, now I'm going to do literally the same integral again. So I should get 10 no matter what I do. Only this time I'm going to compress the x dimension first. So let's see here. What's my leftmost function with x? And then what's my rightmost function with x? Well, the leftmost function of x, or my lower bound, that's just a vertical line for the y-axis. That will be x equals 0. So when I'm setting up my x integral, I'm going to have 0 as my lower bound. And remember, this isn't 0 as a number. This is 0 as a constant function with x. Okay, now let's get the equation of this line right here. But this time it's got to be x as a function of y, since we're doing dx right here. Well, we know before that y was 4x. So if we divide by 4, this line will end up being x is y over 4, as the chat has said right here. So that's going to be our upper bound because that's further to the right, meaning we have higher x values here. Okay, now that we've gotten bounds for that, we crush the x dimension. So we kind of smush this triangle from left and right. And then we just look at what the highest and lowest y values we have are. So let's see, our lowest y value that we have is 0. And our highest y value that we have is 4 right here. So this is going to be our double integral for this. Now, unlike the double integrals where we flipped the order last time and it looked essentially the same, we just literally flipped the order of these. Notice that the bounds on these integrals look significantly different. If you're integrating with respect to y and you still have an x left, you're going to have x's in here. But then if you're integrating with respect to x, you have y's left, you're still going to have that in there. So the integrals will look significantly different if you change which way you do it. So you almost have to kind of redo the problem in order to change the order. But trust me, sometimes it's worth it. We'll see that in a little bit. All right, I'm going to do my x integral of 5, which goes very much the same way that the y integral did. We have 5x, and this is going to go from 0 to y over 4. And then I'm going to plug in y over 4 here. And we have 5/4 y minus 5 times 0, which is 0. And then we go ahead and integrate this. So I integrate 5/4 y to be 5/8 y squared. I do that from 0 to 4. Let's see, I'm going to plug 4 into here, giving me 16. I plug 0 into here, giving me 0. And 5/8 times 16, well, 16 over 8 is 2. And then times 5 gives us that answer of 10 once again. So as you can see from this example here, it doesn't matter which way we do it, as long as we set it up right, you should get the same answer either way. Now in this problem, I don't know. I think maybe this integral was a little bit easier to do. We only ended up with 1 term rather than 2 down here, but these are comparatively the same. I would say whichever way you kind of felt most comfortable setting it up would be the quickest way of doing it. But as I said earlier, that will not be the case for some of these. It's in some cases, it's almost actually, it is mandatory that you do it in a particular way for it to work. All right, so we got that example done. So let's take a look at another example. It's best learned through practice, honestly, just like most things. All right, so we're going to try to find the double integral of x over the region D, where this time D is the region between y equals x and y equals x squared in the first quadrant. All right, well, let's go ahead and draw that. Here's y equals x. We have our diagonal line. And then down here, we end up with y is x squared. And so the region D is the stuff that's going to be inside there, right here. So we just test the integral in one order. If it's too hard, we do it the other way. Yeah, that's right. Usually I would kind of set it up, and then if you see like, oh, this integral is going to be terrible to do, then don't do it that way and try to write it the other way. Well, the next example will be like that. So you'll see what we do. All right. So once again, I'm going to do this integral in 2 different ways. I'm going to do the y dimension first and then the x, and then I'm going to do the x dimension first and then the y here. So let's see. So I'm integrating x, and I'm doing this with respect to y first. Now let's see here. My lower bound for y is going to be a one-dimensional curve. It's x squared. And then my upper bound, the thing giving me higher y values, will be x. Now, often this seems kind of backwards, but remember, between 0 and 1, x squared is the one that's going to be smaller. All right, and then now we compress everything in the y direction down. So we kind of crush everything down to the x-axis, if you will. And then the bounds for that will give us 0 to 1, because these intersect at the point x is 1. All right, so this is going to be our integral right here. And as you'll find doing these, usually the hardest part is setting these guys up. Usually the actual integrals that you have to do aren't really too bad. Like you have to usually just do Calc 1 stuff, maybe a few minor Calc 2 techniques. But other than that, it's usually not too hard. Why is x the term we integrate? Because we're trying to do the double integral of x over dA right here. All right, so let's integrate x with respect to y. Now, we have the same kind of mindset here as with partial derivatives. So when we're integrating with respect to y, x is a constant. So what am I going to put as the result for this integral? xy, that's right. So the integral of a constant, which x is in this case, will be the constant times the variable. This goes from x squared to x. All right, now we're going to plug in x here. We have x times x is x squared, and then we subtract and we have x times x squared, which will be x cubed. All right, how do we get the 0 and the 1 bounds? The lowest x value that we have is 0, and then the highest x value that we have is 1. So remember, we kind of smush. Imagine that you're kind of smushing this picture directly down onto the x-axis right here. All right. So let's continue here. What we're doing, what are we actually, so I think some people are confused about what we're actually doing in this problem. What are we actually doing here? If I were to draw this in 3D, we would have the plane X. And so the bigger the X value is, the higher up we're going to be. So if I were to draw a little mini 3D picture of that, we're just going to have X, Z equals X. It would be kind of like this diagonal plane going up. And what we're doing is we're finding the volume underneath this slanted plane that's kind of going up and out of the page. We're finding the volume of that in this region right here. So we can imagine that this region is kind of a 3D shape. If it projects down right here, we're trying to find the volume underneath this plane that goes down here. All right, so now we need to do this. The integral of x squared will be x cubed over 3. The integral of x cubed will be x to the 4th over 4. All right, so then we plug in 1 here, and we have a third. Plug 1 into here, and then we have a quarter right here. So then we have a third minus a quarter, that'll be 1/12. So the 2D drawing is basically the base of the shape. That's right. Yeah, so this is us looking totally top down on the shape. But then remember, coming out of the page, there'll be a height, and that height in this problem gets bigger the more x we have right here. So the last one represents z equals 5. That's right. So that's just a flat plane. It's just z equals 5. So we're just finding the volume underneath that. All right, we got 1/12 for this. Now let's try to do this from the other perspective. And this will be another one where it won't be too hard to do it either. Okay, so let's see here. So we have our left bound here. X is, well, y was x, so I guess x will be y here. But then what's the other bound going to be here? So if we turn this one into x equals something, what do we get? That's right, we're going to get the positive square root of y right here. All right, so this time when we integrate, our lower bound, remember with x's, the lower bound is the thing that's further to the left. So we're going to have y here, and then the thing further to the right is root y. And then now we look and see what our y values are. So we're compressing things like this now. If we smush this picture like this, the highest y value we get is 1, and the lowest y value we get is 0. So this will also go from 0 to 1 right here. And somehow if we do this, it magically should end up being 1/12 here. So now this time I'm doing the integral of x with respect to x. So I'm going to get x squared over 2 for that. All right, and then I plug in my root y. Wait, why is it square root of y on the top? Because that's what this curve is. Remember, if we're doing the integral with respect to x first, we need x is something and x is something. So this curve right here, since it's y equals x squared, if we solve that for x, we get x is root y right here. All right, so I'm going to go ahead and plug in root y into here. I plug root y in, I get y over 2. And then I subtract when I plug y in. There's y squared over 2. All right, so now I want to integrate this with respect to y. So I have y squared over 4 minus y cubed over 6 if I divide by the appropriate powers. Plug in 0 and 1 into this. And I have a 4th minus a 6th, which lo and behold is also equal to 1/12. So either way, we're going to get 1/12 from this integral, no matter which way we do it. I would say that this way is probably the easier way of doing it given the information here, because they gave it to you as y as a function of x. So if they give you information a certain way, it may behoove you to set up the integral with the way they give it to you, but it wasn't too bad doing it this way either. All right.
Professor Manley, can you explain how to set up the bounds again, please? I got kind of lost.
Yeah, sure. So with this one, we're trying to do the x dimension first, right? So we want to find our left bound, which is x is something, and then our right bound, which is x is something else. So this line is y equals x, so we can just flip the order of that and have x equals y. And then this was the parabola y equals x squared. So now if I want x to equal something with that, I just take the square root of this, and I get that this curve is x is root y. Now this will be my upper bound because it's further to the right, and it'll have higher x values. So I put root y in here, y down there, and then I kind of crush my x dimension here. So if I were to squish this, the highest y value would have is 1, and the lowest y value would have is 0 right here.
Okay, thank you. I understand now.
All right, wonderful. Okay, so I've been warning you guys repeatedly that the integrals aren't always this nice. Sometimes we're going to get integrals that will be impossible one way, but then not too hard at all the other way. So for example, let's take a look at this one. This is the integral from 0 to 1 and root y to 1 of x cubed plus 1 dx. All right, so why don't we try it in the order that's written right here? So let's just try it written the way it is. Okay. Well, let's see here. So immediately we have to integrate the square root of x cubed plus 1. Okay. Does anyone know how to integrate the square root of x cubed plus 1? What technique should we use for that? All right, we're seeing a lot of different answers here. It turns out that this is actually one of those integrals that you just can't do using either techniques in Calc 2 or really any other kind of techniques. If you were to put this on Wolfram Alpha, it would tell you about something called the hypergeometric function, which more or less is a function that mathematicians have invented to be the answer to things like this. So that's not really a satisfying way of doing it either. So unfortunately, this one's a frowny face, and we can't even go in this direction at all. So we can't do the integral if we do x first and then y. That's just not going to work out here. All right, so what we need to do is we need to change the order of this integral here. So let's try to draw. So earlier we started with bounds. So like earlier we had y is x squared and drew that. This time we're going to start from the bounds of the integral and draw the picture that way. So let's see here. So with this one, they're doing x first, right? So they have x equals 1. So that's like right here. So then we have the line x is 1. And then we have x is going to be the square root of y. Well, we actually just dealt with that. We know what that is already. That's a parabola that looks like this. So our rightmost x bound is 1. And our leftmost x bound is this right here. Now we need a little bit more information. We need to know how high or low to go with y's, because maybe we could go down this way somewhere. But our y value starts at 0 and ends at 1. So kind of draw horizontal lines right there. So this is going to be the integral, or sorry, this is going to be the region that we need to integrate over. Now what we're going to do is we're going to imagine this the other way. So we want to try to set up this integral differently. So we want to do the integral of x cubed plus 1, but we're going to do it with respect to y first and then x. Maybe that will make it easier. It's gotta, or else we don't really have an option. All right. So let's see here. What is our upper bound for y? So y equals what is going to be our upper bound here? It's going to be y equals x squared. That's right. That is our top function right here. Okay, and then what about down here? So that was x squared. What about down here? What's our lower function down here? 0, that's right. And remember, it's not just a number, it's a constant function. It's actually a horizontal line right here. Okay, so that we did that. Now, what we want to do is we want to get the highest and lowest x value that we have. So what are the highest and lowest x values that we're going to have here? That's right. We're going to get 0 to 1 with that because we have x equals 0 over here, and we go as high as x equals 1 for this. Where did I get the y equals x squared again? Well, remember my bottom bound here was x equals root y, which was the same parabola that we had on the previous problem. So if I want, if this is x equals square root of y, then I square both sides and I have x squared is y right here. So the bounds of the inner integral will always be functions. Yes, that's right. That's what I'm trying to say. So these will always be one-dimensional curves, and these will be zero-dimensional points. Oops. Let me write it down this way. That's right. And later on, when we get to triple integrals, don't be too scared, we're going to have our first integral be 2D surfaces, and then we're going to have 1D curves, and then we're going to have zero-dimensional points. So we kind of just go down a dimension every single time we do an integral. All right. So now we're going to try to do the integral this way and see if it did any better. All right, so I'm going to do the integral of root x cubed plus 1, but this time I'm doing it with respect to y. Now, it's extremely intimidating to do it with respect to x, but it's pretty much trivial to do it with respect to y. All I'm going to do is I'm going to attach a y there, because root x cubed plus 1 is just a fancy constant with respect to y. All right, let me do this from 0 to x squared. All right, I'm going to go ahead and plug in x squared here. So we have that times x squared. And then I'm going to plug 0 into here, but that's just going to end up being 0 right here. Okay, now we need to, so now the time has come for us to do our x integral again, but this time we have the help of our friend x squared right here. Maybe that will make a difference. So what do you guys think now? How are we going to do this integral now? And it looks like, yeah, it looks like u sub is the choice here. So I'm going to make my u the x cubed plus 1, du will be 3x squared dx. So I'm just going to divide this by 3. 1/3 du is x squared dx. I'm going to work right to left because I'm running out of room here. So this integral, well, let's see, what will my new bounds be? So if I put 0 into here, I get 1. If I put 1 into here, I have 1 cubed plus 1 will be 2. And then I'm going to have square root of u, and then 1/3 du right here. All right. So then what I'm going to do is I'm just going to do the integral of root u. So I raise this to be to the 3/2, and then I divide by 3/2, which is the same thing as multiplying by 2/3. I do this from 1 to 2. So I have 2/9 times 2 to the 3/2 minus 1 to the 3/2, or just minus 1. So there we go. We end up getting this bizarre number as our answer right here. And this ends up being the volume of our integral. So if we were able to do this in some magical way, then we would somehow get 2/9 to the 3/2 minus 1. So sometimes you can actually do integrals backwards by knowing what they are going to be using a different method and then kind of working backwards from there. So even though this integral was impossible to do directly, we still know what it's going to be equal to. It's still going to be 2/9 to the 3/2 minus 1. All right, now, unfortunately, oftentimes we're not going to tell you guys which way to do it. So we may be like, oh, do this double integral, but then you might have to realize on your own, like, wait a minute, I don't want to integrate this. I need to change the order. All right. Let's do another one. So we're getting a lot of good practice here. So we have the integral from 0 to 1 and the integral from 3y to 3 of e to the x squared dx dy right here. Can I show that page again real quick? Yeah, here's the bottom of the page. All right. So I want to do this integral right here. Now, what would be the problem with doing the integral in the way that it is written? Does anyone see a problem with that? It's hard. Yeah, that's an understatement. Yeah, you're not going to be able to do this one without some kind of linear term as a substitution. You can't just do the integral of e to the x squared right here with respect to x. So that's not going to work out the way we want it to. So we're going to have to do things the other way here. So we're going to try to flip the order of integration here. So in order to do that, we need to draw the region of integration and then write it differently. Okay, so our bounds, our first integral is with respect to x, right? So we have x is 3 and x is 3y. So let's draw that over here. So here's x equals 3. So it's a vertical line, looks like that. And then we have x is, or 3y is x, meaning that y will be x over 3. So this is kind of like a slanted line, but it's relatively shallow. So we're going to end up getting this right here. All right. So there we go. And then our lower bound for our region with y is 0. So we're going to be cut off down here. And then our upper bound with y is 1, which is where these guys meet right here. We're doing this over this triangle right here. All right, now we did that with respect to, the original integral is with respect to x right here. So now we want to write this the other way. Let me actually start over here. That might be better. So this time I want to integrate e to the x squared. I want to do it with respect to y first, and then we're going to do it with respect to x. So remember, we need to come up with our y bounds first. And if it's the first thing being integrated, they're going to be curves. So we have y as something as a curve, and we have y as something as a curve right here. Okay, so what is y going to equal? Well, I actually just wrote it already. This line is going to have the equation y is x over 3. And since that's higher up, it's going to be my upper bound. And then my lower bound here will be y is 0. We have 0 like that right here. And then the x's, what's the lowest and highest x values that we have if we crush everything down here? Well, we're going to have x is 0 all the way over here. And it seems like we go as far as x is 3. All right, so this is going to be our new, integral right here. All right. So now, while e to the x squared was impossible to do with respect to x, it's no problem at all to do with respect to y. We have 0 to 3, and then we have e to the x squared y from 0 to x over 3. All righty, let's substitute that in here. So we have e to the x squared, and then we have x over 3. That's what we get for the first part. And then we plug in 0 in here and get 0. All right, now comes time to face again the integral with respect to x, but this time we're equipped with a friend to be fodder for our substitution here. So I'm going to have u be x squared and du be 2x dx here. Now we don't have 2x dx, we actually have x over 3, so I'm going to divide everything by 6 to get that lined up. All right, so I'm going to go ahead and plug this in. So I have e to the u du. I have a 1/6 here. And then what will my new bounds be? Let's see. If I plug 0 in for this, I get 0. And if I plug 3 in for this, I'm going to end up getting 9 right here. All right, so what do we get here? Well, the integral of e to the u is e to the u from 0 to 9. So we end up with 1/6. If I plug 9 in here, I have e to the 9th. If I plug 0 in here, I'm going to get 1. Don't forget about this. I actually was going through the notes earlier today, and like it's really tempting to kind of just skip any kind of 0 bound you see. But especially with exponential functions, you could be missing something here. So don't forget about that -1. So there we go. There's our result for our double integral here. I see you guys joking about like different types of substitutions. I want to talk about something for real that's actually is approximating and that is actually really nice. A lot of integrals like this one back here, like let's say we want to do the integral from 0 to 1 of x cubed plus 1 dx. This integral right here, this is impossible to do, you know, normally, which is the fancy word for it is analytically by using techniques that we've learned in class and stuff. But doing this on a computer, if you write this as a Riemann sum and you just make a for loop on a computer, your computer will spit out a really accurate approximation of this almost instantly right here. So while this is impossible to do analytically or by using exact techniques, it's very simple to do this if you use numerical approximations. And for many fields like physics and engineering, that's totally fine. So oftentimes, even if you can't do something explicitly, approximation is good enough here. All right. So anyways, we got through this one and we were able to do this one analytically or with our techniques, and we got it exactly. All right. So let's see here. Area of regions by double integrals. The area of the region D is A of D is the double integral over that region of 1 dA. Or sometimes you may just see it as dA with no 1 at all. And why does this make sense? Well, what we're doing is we're adding up all these tiny little patches of area, right? All of these dx's times dy's. And if we add all of them together throughout the region D, then we're going to have all of the area throughout the region D right here if we broke it up into all of these pieces. So that's why this formula is the way it is. All right, so our next task with this in mind is to set up a double integral that represents the area of the region bounded by y is x squared, y is negative x plus 12, and y is 4x plus 12. The printer didn't print off the color version, so here is y is 4x plus 12 shaded in. Here's this, and then here's this. Okay, so let's go ahead and set this up. So let's see here. I guess I'm going to do an integral with respect to y first. I think that might be a bit easier here. So I'm going to have my integral of 1, because remember, I'm just finding an area, right? So all I need to do is integrate 1. I'm going to do dy and then dx. Now, the problem here is that there are two different upper bounds for y, right? There's this line right here, and then there's this line right here. So what we need to do is we're actually going to split this up into two double integrals. We're going to find the area of this region right here, and then we're going to find the area of this region right here. Okay, now the lower bound for both of them is this y equals x squared. So that's going to go on the bottom of both of these integrals. All right, and then the upper bound for this one, for the left, is going to be 4x plus 12. And then the upper bound for the right version is going to be negative x plus 12. All right, so let's see here. So now we have our y integrals here. So now we just need to see how far these go in x. So for our left integral here, it seems like the lowest x value we have is negative 2. And then since we're stopping where these curves intersect right here, we're going to go to 0. Now for the right-hand curve here, it looks like we start at 0 where the previous one left off, and then we go all the way to an x value of 3. All right, so there we go. There's our integral right here. And all they asked us to do is set it up. So we don't need to actually do this integral, although it really wouldn't be too hard to do even if we did want to do it. We would just get a y here and then have this minus this, and then we would just do a polynomial integral right here. All right, so that's how we set up this integral. So watch out if your upper bounds change, because then you're going to need to split your integral up into 2. Wouldn't this be possible using Calc 1? Yeah, that's right. It's just an alternative method for doing that. But also in the future, there's going to be some formulas that kind of use this as a foundation that you can find the area in this way, and then they can kind of expand upon that. So it's not just a harder way of doing the same thing we've already done. There's going to be kind of, this perspective is useful for later. All right. So let's see here. let's find the region between two surfaces. So kind of like how you could find the area between two curves back in Calc 1 by doing the higher curve minus the lower curve. In Calc 3, you could simply do the higher surface minus the lower surface over the region where they intersect. So the volume here is going to be our double integral. And if f is bigger than g, we're going to have f of xy minus g of xy. And we could do this in either way. So I'm just going to write dA. When you want to specify that you don't really care about which order you do the integral in, you could just write dA. And the reader on their own can translate this to dx dy or dy dx, whichever is most convenient for the moment. But a lot of times in general formulas, you'll see dA because they don't really care about which order you're doing it in. All right, so set up an integral for the volume of the solid between these surfaces right here. All right, so we got 3 minutes. Hopefully we can do this. Let's see. So z is x squared plus y squared. That one's going to be a elliptic paraboloid. It's going to look like this. And then we can imagine that this is kind of capped off at z equals, wow, that was not good at all for the z. That's a little better, not much. Anyways, let's just imagine this plane is z equals 9 here. Use our imagination. And then this bottom is going to be z is x squared plus y squared right here. All right. So now what's the region that we're going to be integrating over? Well, if we look at this top down, what shape are we going to see? We're going to see a circle. And it's going to be where, it's going to be our biggest possible circle that we're going to have here. It's where these guys meet. So the area of intersection for these will be x squared plus y squared is 9. And that's just a circle of radius 3. All right. So this is going to be our domain right here. All right. Now let's see here. This time, I usually just do it with respect to y first if I can. So this time my integral is not just going to be 1 though. What is my integrand going to be? What's the stuff inside the integral going to be? Do you guys know? It's going to be the other way around. So it's going to be 9 minus x squared minus y squared, because the plane is kind of floating above the shape here. We have 9 minus x squared minus y squared. All right, now we're going to do the y first. So we need to figure out what this is in terms of y, and then what this is in terms of y. So we're effectively just looking for the half circles here. So the upper half circle is y is the square root of 9 minus x squared. And the lower half circle will be y is negative the square root of 9 minus x squared right here. All right. Oh, why is it that way? It's because z equals 9 is higher up than z equals x squared plus y squared. This can have much lower z values than 9. So z equals 9 is going to be our upper bound here. Yeah, and this is a top-down view right here. All right, so that means our y bound up here will be root 9 minus x squared, and our y bound down here will be negative root 9 minus x squared. All right, and then let me ask you guys this. What are our x bounds going to be? What's our lowest x value here and our highest x value here? -3 to 3, absolutely right. This time I think we could have used symmetry if I'm not mistaken. Yeah, we could have, so if you wanted to, you could have used symmetry and done 0 to 3 and then doubled your answer right there. So that's totally fine if you just want to do 0 to 3 and then multiply this by 2, because it's the same on either side of the x-axis here. But once again, this was another integral where we had to set things up, and that's wonderful because plugging these in as bounds is not very fun. So plugging these in for bounds, well, it wouldn't be, no, because we would integrate this to be a y cubed. So then we would have 9 minus x squared to the 3 halves. So We don't want to go down that route. That might be some trig sub if we go that way. Now, one thing I want to say to kind of segue us to the next class here is that there's going to be an easier way of doing integrals over circular regions like this. So you see these bounds are really awful if we have to do it with x and y. But if we call upon our old friend polar coordinates and set up our double integral with respect to that, then these become a lot easier. So that's going to be what we're going to talk about next time, is how to make integrals that look like this a lot easier. All right, so I will see you guys on Wednesday.